Okay, guys. I hope that everyone's back. Can you take a seat, Yeah, so we have Dr. Joseph here. So give me a round of applause.
Thanks very much. So I guess I should talk to you all about quantum computing. So I don't know how many of you know much about quantum computing. Does anyone not know what quantum computing is? Great. Okay, that's good because some of the early slides on this are really, really basic, but there's some more technical slides a little bit further on. Okay, so I guess you're all familiar with the basic idea of a Turing machine. Is that correct or not? Okay, so this is like an abstract model of computation where you have some tape that's having symbols written to it and erased by some head that's moving along the tape, and the head has some set of internal states. And with this, you can implement everything that's computable, any computable function you can implement with a Turing machine. But at a really high level, what this is doing is modeling what you do when you do a computation with pen and paper. Right? So if you have a notebook in front of you, you're looking at the page, you're looking at some subset of the symbols on the page, you just look at one or two at a time. You get some idea in your head because of what you've seen written down. You move to a different part of the page, you scribble some new symbols, and you move back and forth until you've completed your calculation. Right? So this is basically what a Turing machine is capturing. So we know that basically every computing device in this room and most of the ones on the planet work according to basically the same principle. Now, they may be doing operations in parallel, so they may work in a slightly different way, but fundamentally, they're really just mimicking what a Turing machine does. Maybe in a slightly different way, but they're reading some information from memory, for example, making some changes to it, writing it back to memory, and so on. Now, if you think about this, you come to the conclusion that actually there is some amount of physics built into this process. Because it's essentially copying what a person does, you could say, well, maybe everything you can do can't be expressed just as you writing scribbles on a page. Maybe there are other things you could do to the page that somehow this model doesn't capture. Right? And that's when physics comes into the picture. And you say, well, what could you do? What does physics allow you to do that isn't somehow effectively the same as just scratching the page or writing little symbols on it? Is there anything you could do that's fundamentally different? That's not just rearranging the structure of the page. And there's a couple of possibilities. Basically, all of classical physics behaves more or less the same way. So you can see, no matter what you can do, moving objects around on a table is basically the same. You could represent that by writing on a page. You could just record the position of the objects, and that would give you effectively the same thing. You could say, well, what about waves? Well, you could just draw a little picture of what the wave looks like. And so that will give you effectively the same thing. But when you get to the physics of the 20th century, things start to go awry. So in particular, there's two different areas that make up modern physics. There is quantum mechanics and there is general relativity. And neither one of these is really captured in this model, right? I mean, okay, so let's take relativity first. When you're working on a page, in principle, you could throw that notebook into a black hole, right? And that would do something weird, right? It would do something weird with space and time, or you could, you can be scribbling on your notebook and you can take a rocket ship and fly into, or close to a black hole while you're doing it, and that's going to change your perception of time. So maybe you can do some things much quicker than you could otherwise. But actually, it turns out we don't really believe that helps. So at the moment, we don't really think that being able to do relativistic operations would make your computer much better than it currently is. There is a caveat to that, which is that if you can build a time machine, which physicists call closed timeline curves, not to sound crazy. So this is the respectable way of saying time machine. Right? You can't write a paper saying, you know, the implications of time travel for quantum computing, but you can write a paper that says, you know, computational power of closed timeline curves. And that's basically, you know, how you filter out the crackpots versus serious people that want to talk about time travel. Okay, so if you could create closed timeline curves, basically create time machines, then yeah, things go weird and you get grandfather paradoxes and so on, and you can leverage grandfather paradoxes to do computation much quicker than you normally could. You can solve some really, really hard problems with time travel. But we don't really believe that closed timeline curves are possible. And without them, the kind of more conventional space-time that you get doesn't really seem to be very useful for quantum mechanics. Very useful for computation, and it doesn't seem to be accessible at all experimentally. Right? You can do some special relativity stuff by just, you know, accelerating something really fast, but the effects are really, really small, and it's just not something we can easily do in a laboratory. The other area, though, is quantum mechanics. And we can see quantum effects in a laboratory, and we've gotten pretty good at manipulating them at this point. We've got about 100 years experience of doing it. And at this point, you can do really precise quantum experiments. And in fact, quantum field theory, which is just a quantum mechanical theory, is what is the best verified of any physical theory. So it's verified out to like 19 digits or something like that for certain predictions. So it's really, really accurate. It may not be exactly how the universe works on a fundamental level, but it's closer than anything else we've ever found. So the other thing we know is that if you have quantum mechanics, if you can make quantum mechanical manipulation, so instead of writing a 0 or a 1 or a 2 on your page, you write in a quantum superposition, which means that it's not quite the same as a probability. So, you know, you can think of like randomly writing 0, 1, 2, 3, 4 on the page. In quantum mechanics, it lets you do different things, not with different probabilities, but with different amplitudes. And you can think of an amplitude as basically the square root of a probability. And this is kind of a strange thing, but it means that amplitudes can be positive as well as negative. And if a particular event can happen with two different amplitudes, so there's two different ways to get to the same outcome, it can be possible that they add up so that the probabilities increase. But it can also be possible that they cancel out because maybe the amplitudes have different signs. So you can get it in one way with amplitude at, say, 1 over root 2, and you can get it in another way with amplitude minus 1 over root 2. So your total amplitude for getting that outcome is 0. So when you square that, you get 0. So there's no probability of you getting that outcome. So this is a kind of strange wave-like behavior that happens in quantum mechanics. So you get the kind of interference you get with water waves. So if you splash some water here and you splash some water here, you see the waves go along, and they can have either positive amplitude or they can have negative amplitude. And it's possible for the two waves coming in to interfere and cancel out in some places and constructively interfere, so you get a higher wave in other places. And that's kind of what's happening. But the real difference from quantum mechanics from this kind of wave mechanics in the classical world is that the dimension of the space that this happens in quantum mechanics is exponentially large. It's much, much larger than you can do with classical mechanics. So there's a kind of combination of two different effects that lead to an advance for quantum mechanics. I'm going to show you an example of a quantum algorithm, so you'll see an example of how this happens. So don't worry if I haven't made it particularly clear at this point. So anyway, this reasoning gets you to the idea of a quantum computer, which is basically a kind of computing device that rather than storing the information and manipulating it in classical states, 0 and 1, or whatever you want to call it, instead it can manipulate superpositions of states. So the device can be in different classical states. So for example, if it's storing information in binary, it might store the string 0000 with some amplitude, but it might also store the string 1111 with a different amplitude. So it's storing them in superposition. And it's able to manipulate these superpositions. And it turns out if you do this, if you can build such a device, you can do a lot of interesting things. So there's basically 4 kinds of ways this helps you. The first that maybe some of you have in mind when you think of a quantum computer is that it allows you to do certain kinds of new algorithms that are just plain faster and more efficient than classical algorithms. It can, for example, if you could build a large enough quantum computer, you could factor numbers very efficiently. So if you have a large number that's 2 prime numbers multiplied together, you can figure out what those prime numbers are basically as fast as you can multiply them together. And that's a problem because the hardness of factoring is at the heart of the security of the RSA crypto system. You can also compute discrete logarithms, and you can also break elliptic curve-based cryptography. So quantum computers are bad news for a lot of public key cryptography. So that's one application. That's one area. Another area is that you can, if you have several quantum computers that are networked together, so they can exchange quantum states with one another, they can accomplish certain kinds of tasks, certain kinds of computation with less bandwidth than you could do classically. So they can compute the same things with less communication than you would need classically. You still need some communication most of the time, but there can be an advantage. A third property is that, again, if you have this kind of network of quantum computers that are communicating quantum states, it turns out that there's a particular property of quantum states, which is that you cannot perfectly distinguish them. If you make a measurement on a quantum state, it disturbs the state, so you can't make another measurement on that state and still get the outcome you would have had the first measurement not being made. And this lets you come up with new forms of cryptography that rely on physics for their security. They just rely on the correctness of quantum mechanics rather than on any computational assumptions. So I mentioned before RSA, which relies on this assumption that it's hard to factor 2 numbers. With quantum cryptography, a lot of it is its security is derived purely from the laws of physics, and there's no computational assumption involved. Unfortunately, we can't use this to solve all the kind of cryptographic problems we would like, but we can do certain ones like key exchange. So that's 3 applications. The fourth is if you have a quantum computer, you can deal with quantum data. So this may sound strange, but one of the things that has had a big change on the computing industry has been the need to process or the ability to acquire digital information, right? So we all have digital cameras now, right? You don't have to like draw a little grid on your picture and assign a number to the color for each little grid square and then type it into your computer. You can acquire the information directly on a digital camera and copy it straight to your computer. Right? So because you can do this, you can just capture information digitally and straight into the computer, and it doesn't really have to go through you as a person, right? It's just directly acquired and into the computer. But the world isn't digital, right? The world around us, it's not represented by some binary information that we can just sample with our digital camera. It's not taking an exact copy of the state of the world at that point. Rather, the physics that governs the world around us means that the information describing the world around us is necessarily quantum mechanical. And so if you want to make the most accurate sensors you can, then you need to be able to record the quantum state. And that having quantum computers gives you a way of directly interacting with the quantum state of a sensor, and hence giving you a way to interact with the quantum state of the world around you without collapsing it into classical information. And this is kind of useful because it turns out you can build much better sensors using quantum mechanics than you can classically, both for just measuring things like magnetic fields, but also for imaging and things like this. Now, we're a long way from being able to implement some of the imaging protocols, but it still gives you an idea of a reason you may want quantum computers. You may want them simply because you have quantum data that you want to be able to process. Okay, so I'm going to show you a couple of slightly technical slides, just to give you an idea of the basics of quantum computing. So in quantum computing, the basic unit of information we have is something called a qubit. And a qubit is just, you can think of it as a quantum equivalent of a bit. That's why we call it a qubit, because it's a quantum bit, which means that it has two classical states. So it can be either 0 or 1. Okay, because that's the minimum number of states we need in order to be able to represent more than one state when we put them together. Okay, so a qubit has a couple of it's quantum mechanical, and that means we need to be able to allow it to be in a quantum superposition. So for each of the two states, 0 and 1, each of the two classical states, a general state of the qubit, you need to assign some complex amplitude to A, and some complex amplitude to the 0 state, and some complex amplitude to the 1 state. Okay, so a general state of a qubit is just described as this, as some complex amplitude for 0 and some complex amplitude for 1. So this gives you 4 different numbers that describe it, 4 different real numbers. There's a real number associated with the real part. So okay, so I'm going to write a quantum state psi, and physicists put quantum states inside these things called kets that look like just a straight line and then an angular bracket, and all that means is it's a vector, basically. It's called Dirac notation. Physicists use it all the time. Everyone else wonders why we use that to denote a vector. But basically we're saying it's a vector in a two-dimensional vector space, a two-dimensional complex vector space. So we can write this out in, say, the standard basis as some alpha times the vector 1, 0 plus some beta times the vector 0, 1. Okay, so that's all our amplitudes are. They're just telling us the coefficients in front of a standard, in front of the standard basis vectors that we need to describe the vector that represents our quantum system. Now, there's some kind of important properties. One is that the vectors always have unit length, and this is because I said that these amplitudes, alpha and beta, can be interpreted basically as the square root of a probability. This isn't really accurate. What I mean by this is that alpha by alpha star is a probability. So when you multiply alpha by its complex conjugate, you get a probability. But basically, we're requiring that alpha squared plus beta squared equals 1. So that means that the length of the vectors needs to be 1. Okay, so if you do this, it turns out that you've got these 4 numbers you need. You need the real part of alpha, you need the imaginary part of alpha, you need the real part of beta, and you need the imaginary part of beta. But it turns out that we don't care about the global phase. So if you multiply your vector by any complex number, it doesn't matter, it doesn't change the state of the system. You can't ever measure what that number is. There's no experiment you could ever do that tells you what that complex phase is. So it means there's only really 3 numbers we care about. We only need really a real number to describe the amplitude for alpha, and then a complex number for beta. And because of this, we can kind of draw what the states of a qubit look like in 3 dimensions. Okay, and this is something called a block sphere, which is a way of drawing the state of a qubit. So I've drawn 0 as pointing up, and 1 as pointing down. Although 0 and 1 are usually orthogonal vectors, so they would be at right angles in general. But this is just a kind of an odd way physicists represent it. So we have 0 on top, 1 on the bottom, and anywhere on the surface of the sphere, that's a valid quantum state. And if you were to measure that qubit along the z-axis, so you measure it in the standard basis, then the probability of you getting 0 is just given by alpha, well, the modulus of alpha squared, and the probability of you getting 1 is given by the amplitude of beta squared. And the basic operations you can do to a qubit basically involve rotating around each of these axes. Rotate around the x-axis, rotate around the y-axis, rotate around the z-axis. So these are the basic kind of single qubit manipulations you can do. If this sounds confusing, don't worry, you don't really need it later on. I just thought I'd give you an explanation of what quantum computing really is. When we put several qubits together, then the number of states, the number of distinguishable states, increases exactly as it would if we were putting bits together. So if we have 7 bits, then there are 2 to the 7 possible states. If we have 7 qubits, there are 2 to the possible, there's 2 to the 7 distinguishable states. So 2 to the 7 classical states, and each one of those has some complex amplitude associated with it. Okay? So this is what I mean by the size of the dimension of the system growing very quickly. So as we have n qubits together, there are 2 to the n possible states, and there's 2 to the n possible there's 2 to the n amplitudes, one associated with each one of those states. It turns out that in general, the superpositions that we can reach do not always allow us to write a separate state for one qubit and another qubit. So I drew that picture of the block sphere on the previous slide, and I said any state of a single qubit is just some point on the surface of that block sphere. That's true, but if I have 2 qubits together, I can have a state that is just some superposition of 0, 0 and 1, 1, and that you can't write as a state of one qubit and the state of another qubit. There's just no way to separate them. Okay, and these kind of states we call entangled states. And they're quite important in order to see a speed up in quantum computing. You need to exploit these these entangled states. Okay, so that's basically all I'm going to say about what qubits are. But there are a couple of implications of this. One is that quantum information can't be copied. All of the operations you perform have to preserve the length of this vector, and that means all of the operations you perform turn out to correspond to multiplying the state vector of a system by a unitary matrix. And this has a bunch of implications. So quantum information can't be copied. It's also, given a single copy of a quantum system, it's impossible for you to tell for sure what the state is. It also means that there's this way that quantum computers are described to work a lot in news pieces, which is that they try every possibility in parallel and then just weed out the right answer. That's not how they work. In certain cases, you can try different things with different amplitudes, but that's a little bit like just flipping a coin and deciding which computational branch to go down with some probability. The only difference is that amplitudes aren't probabilities, and you can get interference. Like being able to just try each possible branch of a computation and then picking out the result is not something you can do with a quantum computer. Okay, so the kind of basic logic gates we use to build it up, there's a bunch of them. We need some single qubit gates. I won't really go through what they do. But you can think of them as just rotations about this block sphere. So if you have a single qubit, they would rotate it in different ways. These two rotate about the z-axis, either by pi over 4 or by pi over 2. And this gate on top does a kind of rotation about the y-axis, and then it reflects around. But it's just two rotations put together. So these are called Hadamard gates, phase gates, pi-over-8 gates. Doesn't really matter what they do, but in order to be able to build a quantum computer, you need to be able to do some or all of these gates. So that gives you, if you have the tree of these gates, you can do any single qubit rotation by making a long enough sequence of these. You can arbitrarily approximate any operation you could do on a single qubit, any manipulation, any rotation of a vector in three-dimensional space. However, to make a full quantum computer, to make a full quantum computer, you need to be able to do, you need to be able to interact two qubits or more. So that means conditioned on the state of one qubit, for example, you may want to flip the other one from 0 to 1. So if the first qubit is 0, you do nothing to the second one. If the first qubit is 1, you flip the state of the second qubit from 0 to 1. Or you reflect it about the z-axis or something like that. So this does exactly that. If the top qubit is 0, it flips the bottom qubit, and this one, if the top qubit's 1, it flips the bottom one. If it's 0, it does nothing. The bottom one does a similar thing, but instead of flipping the qubit, it rotates by a different axis. It doesn't really matter what these do. The point is you need hardware to realize them. Right? So this is something that's been happening for a long time. People have been trying to come up with ways to implement a quantum computer, to be able to implement these basic gates, to be able to represent information in a quantum superposition, then to be able to apply these things like a Hadamard gate, pi-over-8 gates, and being able to interact them with these kind of CNOT gates and different things like that, and to create the kinds of entangled states we need. There are a number of different approaches to this. The most easy, the earliest one to be looked at, well, there's probably two. One is with trapped ions. So that's you take an atom, you knock off an electron. Now it has an electric charge, and because it has an electric charge, you can hold it in one place by rapidly changing the electric and magnetic fields it experiences. So if we do this, we can trap many such ions in a device called an ion trap. Often they're trapped in a line, but there's a number of different ways of doing this. This is a picture of a surface trap, which instead of trapping them in free space, it traps them just above the surface of a chip. These surface traps are relatively new. It used to be done essentially completely in free space before, where you have some electrodes coming in from the side and maybe some planes coming in at different directions, and you trap a string of ions in between them. So that started happening in the mid-90s. People started playing around with these things, and they've gotten increasingly better at doing it over the years. People also tried using atomic nuclei, particularly in molecules, using nuclear magnetic resonance techniques. And that was used kind of in the early days, but it's not very scalable. So you get to a device of about 5 qubits, and you can't go much further, maybe 7, and then you're stuck. But the new candidate that's come along in recent years that's really changed things has been the use of superconducting qubits. And these are basically little loops of wire that are cooled. So they're basically a little LCR circuit. So they're a loop of wire that has a capacitor in it and a resistor in it and an inductor in it, and they're cooled right down to very, very low temperatures so that the wire becomes superconducting. And you can use these circuits to trap single lines of magnetic flux, and you can use that to represent information. So you can either trap a flux line or not, and doing this you can use it to represent 0 or 1 in your device. And so this is 9 superconducting qubits in a device from UCSB. So this was a few years ago. But superconducting qubits only started to become possible to couple several superconducting qubits together, so you can perform these 2 qubit gates. Only started to become possible around 2007. Before that, the ability to do this was really limited. And since then, people have gotten better and better at doing it. So at this stage, superconducting qubits are starting to emerge as the leading candidate for quantum computing. There are a bunch of other approaches. You can try and do it based on purely on optical systems. You can use individual photons of light, but that has really high overhead. So it doesn't seem to be a very promising approach. There are some approaches based on silicon, but they're kind of in the place that superconducting qubits were maybe 10 years ago, that if they can get two qubits to talk to each other well, then maybe they can build a scalable device, but they're still at that problem. There are devices based on defects in diamond lattices. So you have a little diamond, and in that diamond, one of the carbon, diamond is just an arrangement of carbon atoms, and sometimes they're not always where they should be. And sometimes it traps something like a nitrogen atom instead, and you get a defect in the diamond. And you can use these color centers, so they give the diamond a particular color, depending on what the defect is. And you can use those color centers to store information as well. So this is another approach we've been pursuing. So there's various different approaches people have been pursuing, but the leading contenders at the moment are superconducting qubits and ion traps. And these look really nice. They're little small little chips about the size of your thumbnail. So it looks great. Let's put one in your mobile phone. The only problem is that you have to surround them with stuff. So this is what it actually looks like. So the chip is way down at the bottom of this thing. This whole structure here is something called a dilution refrigerator that's used to cool the chip down. I should say, you could say, well, how is it going to cool it down when it's at the bottom here with all these people around it? That's because the shielding is off this thing. There's usually a big cylinder that comes down around here, and it's usually full of liquid helium. So the very bottom of it is at millikelvin, something like 30 millikelvin, so it's really, really cold. And some of the upper stages are something around 2 Kelvin. Okay, so this all sounds great, but it's been a bit of a slog. So I started my PhD in this area in 2004. And at the time, the maximum number of qubits in a system, I think, was 7. So there was 7-qubit NMR quantum computer, and well, I say quantum computer, it's like a beaker full of liquid, and each one of those molecules is being used to process the information, and it's doing many, many copies, just like one on each molecule. And it's inside a giant spectrometer. So it's not really a quantum computer, but it's something that you can do quantum processing on. The only problem is that what I said before about these things being vectors, the state of the system is described by a vector that, well, if there's 7 qubits, it's in a vector space that is 2 to the power of 7 dimensions, and 2 to the power of 7 is not very large. It's not a big number. Right? So I guess it's 128, right? So if we're multiplying 128 by 128 matrices together, our laptops can do that really quickly. We can't do it by hand very quickly, but a laptop can do it, your phone can do it. Pretty much anything that has a universal processor in it can probably multiply together matrices of that size these days. I mean, I guess you could get some chips with a few NAND gates on it and not be able to do much with them, but basically everything can multiply matrices of that size. So in order to get to a place where it's hard to do this, you need for the vectors to be larger than what you could reasonably store in RAM, for example. And that means you need it to take, for example, billions of bits to describe it, so that you're now talking about maybe gigabytes of memory that you need. So how long does the vector need to be for that? Well, the vector needs to be, a couple of, well, maybe dozens of billions long. So what does that mean? It means you need 2 to the power of 30 something, right? And if you have I have a simulator I coded up for my computer in MATLAB, it will simulate a device with 28 qubits without too much difficulty. If you give me something that has 34 or 35 qubits in it, I would need to try something a bit more sophisticated, or need to try to run on a cluster. At the moment, the record for the largest device simulated is 64 qubits, and that's only for low-depth circuits. And it's using a lot of tricks that let you kind of reduce the difficulty of the computation if the depth of the circuit is low. So if you don't do a computation very many gates deep. So that means we need to hit maybe 50 qubits before there's some kind of break-even point, before your quantum computer is doing something you couldn't do on a larger computer. Maybe 64. If you have a 64 qubit device, a 65 qubit device, that's more than has been simulated, as long as the noise rates are low enough. So starting out, it was about 7, and things look kind of promising, because if you look at this curve, you maybe kind of draw a line on it, and you think it's going to end up somewhere here. Maybe about now we should be reaching this threshold where the devices are of enough complexity. Except the curve is a bit flatter than that. So, well past 2010, 2012, 2013, the most complex devices were now 16 qubits in ion traps. But still, it's a long way from something that you can't simulate. However, in the last 18 months, things have gone a bit crazy. And the size of devices has gone up really, really quickly. And actually, I should say, it's even sharper than this, because there is a data point from earlier this month that I have left out that is like somewhere up here. Okay, so what's been happening is that there's been a lot of focus on making the qubits better and better and better. So if you want to build a quantum computer, one thing you don't want to happen is whenever you try to do a gate, an error to happen to your qubit, like it just randomly gets moved somewhere other than the place you want it to be. The state vector ends up pointing the wrong direction. So there's been a lot of effort on decreasing that error rate. And even if you leave a quantum state alone, even if you prepare an ion in a trap and you walk out of the room, you don't do anything to it, it still drifts over time. So the vector ends up pointing in a different direction than it's supposed to be pointing. And that's a problem. So that's like if your computer chip was just randomly flipping bits at a certain rate. And so actually that does happen in your computers. So very, very occasionally, cosmic rays, which are little charged particles that come flying in from outer space, they hit your RAM and they cause a bit in RAM to get flipped. But this happens very, very occasionally. So most of the time, hardware manufacturers don't bother dealing with this at all, and they just let it happen, and maybe it crashes your computer or something. But or maybe it just corrupts a file in one bit. But sometimes, if you're running really really complex computation, that means you're going to have to leave the computer running, leave a cluster running for months at a time. Then you need to actually implement error correction to protect against this. For quantum computers, the error rate was more like 20% of the time something was going wrong in the early days. So over time, since since '95, I guess, was kind of the first data point for quantum computing, the number of qubits has kind of increased on this log scale, and it's pretty close to a straight line. So it gives you kind of Moore's law, but the doubling time has been roughly every 5 years. And that's much slower than the progress in semiconductors, where there has been a doubling since the late 70s of once every 18 months or so, that the number of transistors in the device has been doubled. But part of the reason for this is that the qubits have been improving during this time. And at some point around 2012, people started to hit the threshold for the error rate below which we can actually actively error correct it. So it should be the case that that for certain devices, the quality of the gates, the noise levels are now low enough that you could start to try to correct errors as they happen by encoding your computation in some kind of redundant way, and then actively checking whether you're still in that encoding, and if not, trying to repair the encoding. So if we could do that, we could extend the lifetime of our computation arbitrarily. We could avoid errors occurring in the computation. And so in some sense, that's giving people the confidence that, okay, qubits are pretty much good enough at the moment. Let's try to build bigger devices. Let's try to increase the qubit number so that we actually have enough qubits that we can start doing this error correction. So that's what's been kind of happening. So if you look at the last 18 months, the doubling time has gone down from something like 5 years to roughly every 6 months. And you see a bunch of devices from commercial companies, which wasn't the case before. It was usually academic groups or occasionally government labs that had been building things. And so you see these are kind of qubit numbers on a log scale again, starting from the end of 2016 and going up to the first, sorry, this should be 2018. Sorry, that's a typo. Okay, so you have devices from IBM, Google, Rigetti, and Intel. So this point here, I think, is 22 qubit device from IBM, and I think this was a 5 qubit device from. Sorry, this is 22 from Google, and then this is a 5 qubit device from IBM, and they've increased really rapidly. So this latest. Yeah, okay, so this point here was a 17 qubit device from, oh, sorry, this is 50 qubits from IBM, yeah. So actually, I may not be able to properly identify all of the data points. Okay, but basically, things are doubling now kind of every 6 months. So there's a lot of excitement in the community because we're getting to that stage where you think that there are enough qubits in the device that you can't simulate it. So you should be able to hopefully use the device to calculate things that you couldn't otherwise calculate. The other thing is that the noise has also gone down in this kind of exponential way. So the doubling time for the length of time your computation can go without an error happening has also increased this way, and it doubles roughly every 0.9 of a year. And it's done that consistently since the mid-90s. So we don't have any particular reason to believe that the quality of qubits won't continue to increase. Okay, so I thought I'd show you some examples of things you might find interesting. So IBM, so this is from May of last year. So in May of last year, IBM announced that they had 2 new processors. One was a 16 qubit device, one was a 17 qubit device. Actually access these, at least you can access the 16 qubit one over the internet. There's a little interface like this, where your qubits start off in the state 0, and you can do Hadamard gates, or you can do C0s and Ts and so on. There's a little web interface. You can drag and drop your circuit, or if you prefer, you can try to code it up in a very basic assembly-like language that you have. When I say very basic, I don't mean to detract from this. All of the languages people have developed for quantum computing at the moment is at a very elementary stage. So it's all basically assembly language where you're saying what instruction for the device to do at every single point. And then, so this was the state of the art 10 months ago. And as of 2 weeks ago, actually less than 2 weeks ago, so 5th of March, Google unveiled the fact that they had a new processor that they built, which has 72 qubits. So it's kind of superconducting qubits have gone from like 17 qubits to 72 qubits in something like 10 minutes, which is kind of interesting because this is now in the range where you probably can't simulate it. Now, there's not any scientific papers out on it yet, so maybe it's too noisy, but certainly the number of qubits are good enough. And the rates of errors for some of the Google chips have been low enough that you would expect that maybe this can do some stuff you can't simulate. But what's kind of interesting is if you start extrapolating from here, and you say, oh, at that point, we could really have some significantly complex devices that can start to do active error correction or something like that. So you can start thinking, well, maybe this is a real technology that you can do stuff with. But one thing to keep in mind is that really these things are like the very, very first computers. So this is a fundamentally new type of computing, but it is analogous to classical computing in the way it's developed. And the devices we have now are still really noisy, and they have really, really small amounts of memory. So they really are analogous to the very, very first computers. If you run a program on the IBM Q device, which you can access over the internet, I'll give you the address at the end. It's just the interface I showed you a second ago. It will get the wrong answer with non-zero probability. And if you have like 10 gates deep, it will get the wrong answer with like high probability, right? So it's going to make errors. And so one of the things we need to start considering is how best to circumvent those errors. One method is active error correction, but we could also try to come up with algorithms that are tolerant to these kind of errors occurring within them. But this is going to be one of the bottlenecks of using near-term quantum devices. They really have errors happen at a non-zero rate. So a lot of the time you're going to get incorrect results, and so you need to come up with ways of dealing with that. Another barrier that that kind of faces us is that there are not that many different applications for quantum computing that are known at the moment. So these are some of the main ones. You've got in 1994, it was the first factoring algorithm was come up with. So it was realized that you could break RSA and various other crypto systems. There was also a simulation algorithm that let you simulate other quantum systems with a quantum computer. Then 2 years later, a fast search algorithm was found. So if you have some list, for example, you take a telephone directory and you want to search the telephone directory, but instead of searching the telephone directory by name, you have a phone number and you want to find where in the telephone directory that number occurs. If you try to do that, you have to look at basically every entry in the telephone directory. And on average, you're going to have to look at half of the entries in the telephone directory before you find the name corresponding to the number you have. But quantum mechanically, there is a quantum algorithm that lets you find this number, only searching through a square root of the number of entries you need. So if you have a disordered database, you can search it in essentially square root time rather than linear time. Then a bit later, around 2000, some optimization algorithms were come up with, and then a big kind of change around 2009 was the introduction of a fast algorithm for solving some linear algebra problems. So if you have some linear system of equations, you could essentially solve that in logarithmic time rather than polynomial time. So that's really useful. There are some caveats that come with that I won't mention, but it turns out you can use this for a bunch of things, and this has kind of led to the emergence of a bunch of quantum machine learning algorithms. So you can use this kind of linear algebra algorithm at the heart of a bunch of different algorithms for different things like support vector machines. Something we've worked on is Gaussian process regression, but a bunch of different machine learning methods can be sped up using this kind of. There's also been some more work on optimization algorithms and so on. But this is still not that many applications. And you can say, well, what's the reason for this? And one reason is that quantum algorithms aren't very intuitive. So I kind of told you a little bit about what qubits were and what the basic gate operations you have are, this Hadamard, the T-gate, the S-gate, and these 2-qubit gates control NOT and so on. And given that information, okay, you can look at the slides again afterwards if you want, but can you come up with a way to use them to compute something quickly? And it's not really obvious how you do that, right? There's a okay, you need to use these kind of interference effects you get in quantum mechanics, but we're not really used to interference effects. So we don't really have a great intuition for it. So if I lost my keys, if I came up here, I knew it was in one of the seminar rooms, but I didn't know which one. I guess the most naive algorithm you come up with for how to find your keys is like check every room, one after the next until you find the keys, and don't go to the same room twice. It doesn't really matter what the order is, right? That's basically the best classical algorithm for searching this disordered database. You just look at entries, don't look at the same entry twice. The order of them doesn't matter if you don't know which, if they're kind of uniformly distributed. The optimal quantum algorithm is not at all like that. You say, well, I'm going to check these all I'm going to start with an equal amplitude of checking each room, and then I'm going to come back to the same place. I'll do some kind of strange interference effect, and then I'll do the same thing again, and I'll repeat that the square root of the number of times that there are seminar rooms, and then somehow magically I will have found my keys. So this is kind of like a geometric depiction of the algorithm, but I won't go into how it works at all. But it turns out that this is how a quantum computer can solve that problem. But how on earth do you come up with that? Right? So we have this kind of intuition gap for quantum computers. Now, I say how on earth do you come up with that, but someone did come up with that because we know it now. But that's one of the problems we face, that it's kind of difficult to come up with. Another problem that faces us, the reason that there's not so many, is that I did a search a while ago for the number of papers that said new quantum algorithm or novel quantum algorithm or introduce a quantum algorithm. So to try to find roughly the number of papers that propose some kind of quantum algorithm. And it turns out the number of results I got was like 570, something like that. I also had a look at the number of GitHub accounts, which is maybe a kind of proxy for the number of people that work on software development at the world. And it turns out that there is something like 57 million active GitHub accounts. So the difference in the number of people writing quantum algorithms to the number of people working on software development seems like it's at least 100,000 to 1. So there is simply not very many people that are working on applications for quantum computing. So this is another thing contributing to this difficulty. Okay, but there is some reason to be hopeful. So if I kind of expand out this timeline of quantum algorithms a bit more, put in a bit more detail, and I expand out the kind of timeline of classical algorithms in the 1940s, say 1940s to 1960s, you see actually the same kinds of problems. The kind of factoring algorithm, well, that's kind of code breaking, right? And there was a lot of code breaking in the 1940s. It also makes use of a quantum Fourier transform, and again, the fast Fourier transform was introduced in 1942. So there's a bunch of algorithms based on fast Fourier transform. Then the optimization algorithms, you see kind of similar things. There was simulated annealing in the early 1950s, as well as the simplex algorithm, which was 1947. Even things like machine learning, which you think, oh, well, that's a really new application. It's been around for ages. So the first paper on neural networks is the one that introduces the McCulloch-Pitts neuron, which is from 1943. Which is maybe a lot longer than you may think, a lot older than you may think. So it seems that one of the things that's happened with quantum algorithms is that we've kind of come up with algorithms for the same types of tasks that people came up with algorithms for in the 40s and 50s. So maybe the reason we're not coming up with all of these different things is because really it's not just a factor about quantum algorithms being hard or there not being enough people or something like that. Maybe actually it's just that the kinds of people that work on these things are the kinds of people that are interested in certain types of problems, and that leads you to come up with certain kinds of algorithms first. So you can kind of look forward and say, well, what might happen next? You know, if we're down the end of the 1940s or something like that, you know, what should we do in the future? What are the problems we should start working on in quantum computing? So you can kind of go to Wikipedia, look up a timeline of computer history, and you can see, you know, what were the big innovations in computing in the 50s and 60s and 70s, and you can say, well, maybe that's what's next for quantum computing. And this is probably true. So, well, I say probably, I think it's probably true. Others may disagree with me a lot, but we're missing high-level languages. All of our languages are basically assembly at the moment, and that makes it really difficult to cook up algorithms if you don't have high-level operations and if you don't have data structures, which we don't. The types of quantum computers that are currently being built are not stored program devices, rather they operate as a coprocessor. So you have some classical computer that operates your quantum computer and interprets the results of the quantum computer. But it's not unreasonable to think that stored program quantum computers should be a fairly near-term step. There was error-corrected memory introduced in 1951. We still don't have error-corrected quantum computing. There have been one or two kind of demonstrations, but the devices are not actively error-corrected yet, in general. We don't have compilers. We don't have networks of quantum computers. There have been a few demonstrations. So in University of Maryland, for example, they have some ion traps that they're able to entangle together. And in Delft, they're starting to interact diamond over long distances. So they have you can think of it as like a little diamond processor in one place and a little diamond processor in another place, and they get to do quantum communication between the two, and you can start to use these to build a kind of quantum internet. And if you can do that, that opens up a whole range of new applications. But in a sense, for quantum computing, looking at the history of classical computing maybe gives you kind of a roadmap for what's ahead in the years to come, because we're not building devices that are equivalent to the laptops you have now. We're very, very far from that. The next devices that will be built, they're more like the computers of the 50s, 60s, 70s. So we still have a lot to learn. Quantum computing may be moving slower, it may be moving more quickly. I'm hoping it's moving more quickly than classical computing, but there's a lot of interesting things ahead for us. So if you're interested in learning more, I'd really recommend this book, Quantum Computation and Quantum Information by Nielsen and Chuang. It's really accessible for people from different backgrounds because there's 3 introductory chapters. One introduces CS and one introduces physics, or the relevant physics. So it's worth looking at the two. And if you want to play with an actual quantum processor, you can go to this URL. This is one of the IBM devices, or rather 2 of the IBM devices that they have hooked up to the internet that you can run jobs on at the moment. There's no cost. You just set up an account for free, and you make your circuit. You hit execute. It takes a little bit of time. Maybe it has to queue for 5 minutes before it runs on the device, but it will run it on a real device made out of one of these superconducting processors, and it will give you back the answer. You get in an email, or you can download it from the website. Gives you a way to try to see how these things behave. Okay, thanks very much.
Can you do conditionals, or like something equivalent to conditionals with quantum mechanics?
Sure. So the C0 gate is essentially a conditional gate. So let me show you what a quantum circuit looks like. I kind of skipped over that a little because I realized my slides here were out of order. So the way we represent a quantum computation usually is we write down the initial state of the qubits. So in this case, I assume all of the bits in my device are in 0, and then each of these little symbols represents some operation that's applied. So in this case, it's a controlled NOT gate, which means the qubit. So you read this from left to right. So the qubit that starts here, if it's 0, you do nothing. If it's 1, you flip the state of the second qubit, of the target qubit. So that's doing a conditional operation. It's doing a conditional NOT gate for a very, very simple condition. There are more complicated gates like this. So this is called a Toffoli gate, or a controlled NOT gate, and that will flip the state of this qubit, conditioned on both of these two qubits being 1. So the two of them need to be 1. And it turns out even if you just have this gate alone, it suffices to do all of classical computing in a reversible way. So it essentially gives you the equivalent of a NAND gate. So with enough of them, you can compute whatever you want. So you can do whatever kind of conditional you want. The only place you have to start being careful is when you start thinking about doing loops, for example. Because if you don't know how long it's going to run, you're going to need to make a measurement to determine whether you should stop the computer or not. And when you make that measurement, it disrupts the state of the system. So there's some subtlety around computation when you don't know how long it needs to run for. Yeah.
How do we know that the errors will be bounded or controlled as the size of the circuits get larger?
We don't know. We don't know, but we've pretty good indication. So, sorry, wrong way. Okay, so this is the error rate for superconducting qubits over time. So, this is the coherence time. So, the amount of time the qubit could live without an error happening. Let's assume there's no gates. You're just leaving it alone. This is the amount of time a single qubit would survive. So it used to be in the late 90s, it was 1 nanosecond. And since then, it's gone to like 10 to the 5 nanoseconds. So like hundreds of microseconds. This does not guarantee that this curve will continue forever. But actually, we don't need it to. As long as the errors happen independently, then things are okay. Unless there's some kind of collective event where all of the bits flip at the same time, or something like that, then we know we can actively suppress errors once the error rate is below about 1%. And a number of systems have kind of hit that threshold, where they're kind of at the 1% range of errors, or like 0.5% or something like that. The IBM devices, you can look at calibration information. It recalibrates every day or something like that. And the error rates for those go from like 2 to 5% or something like that for the C0 gates. But the Google 9-qubit device, I think, had about 0.5% for the error rate. And ion traps, the best ion traps are, maybe 0.3%, something like that for the error rate on 2-qubit gates. Readout is a bit noisy, so when you make measurements on the system, you have quite a high chance of getting an error still. It would be much better if we were way below the error correction threshold, because the closer you are to that threshold, the more resources you need to correct errors. So if error rates were like one time in if errors occurred like 1 in a billion times, then we wouldn't need very many resources to correct them. But when they're happening kind of like 1 in 200, 1 in 500 times, then it's quite resource intensive to correct them. Now, it is possible that there are collective errors that happen that somehow would prevent us from being able to build a device, but that does not seem to be the case, just from the kinds of things that happen. Now, you can't rule them out entirely, just as you can't rule out that my computer won't fail. Because although you could say, well, the processor is very well characterized and you virtually never get errors, and when you do, it's like cosmic ray or something and you get 1 bit flip. But that neglects the fact that I could be walking across the room, I could trip over a power cable and drop my laptop and destroy it, right? So there's a giant collective error that happens. Just in the same way that there is no amount of experimental evidence I can obtain that rules out the possibility that someone accidentally triggers a fire alarm that short circuits a bunch of electronics. right? It is possible to have these collective error events, but they seem to be rare enough that we don't really need to worry about them too much.
How many additional physical qubits do we need to produce like a logically error-free qubit, assuming like 1%?
So the smallest, quite a lot. Well, 1% you're like right at the threshold, which means you need, approaching infinite.
Oh, okay.
No, but if you go down a factor, so there's a couple of efforts underway at the moment to build something that people are calling like a logical qubit. That is basically a qubit that you can store and will never decode it. And okay, you can't guarantee that the life of the qubit is forever. Actually, eventually it will disappear, but you can extend the lifetime so it's longer than the expected lifetime of the universe. And if you can do that, that qubit's pretty good. Now, that is based on this kind of independent errors that you've measured in the lab. You can store it for years and it'll be fine, but it doesn't account for the fact that a meteor could strike the lab and then you're wiped out.
But how much redundancy do they?
Yeah, so for that, maybe you need a couple of hundred qubits. Maybe kind of at the way people are projecting things at the moment. But it's kind of hard to say. It really depends on how close you are to the error correction threshold. It depends on what code you need, what code you use. It depends on your processor architecture, on exactly what qubits are connected to what qubits. It depends on a lot of things. 3% is actually the highest that can be tolerated that we know of, but basically all of the practical codes are like just below 1% or less. So you don't want to be at 2% at all. It's much better to be at kind of well below 1% for your error rates, and it would be much better if we were below 0.1% or 1%. Then things would really become much easier. But I should say single qubit gates have become really good. So ion traps, the error rate for single qubit gates is like 6 nines at the moment. So it's only 1 in a million times that some error occurs during a single qubit gate. 2 qubit gates are less good though. They're a couple of times in 1,000, and that's where you're more in the danger zone.
In analyzing classical algorithms, we usually use like some kind of formalism, like Turing machines, and whether it decides the language or not. Does this formalism of analyzing classical algorithms does it capture the specificity of?
So there is a different model. I guess you're talking basically about complexity theory.
Yeah,
so you want to distinguish because a Turing machine doesn't well describe how my computer works.
Yeah.
Right. It doesn't capture a linear factor, for example. So there's only some polynomial relationship between the performance of my computer and the performance of a Turing machine. Okay. So yeah. So if we want to decide between, so if we have a problem that is in P or an NP or whatever, some different complexity class, and we find that by probably inside the Turing machine or polynomial time or something like that. You can do the same thing. You can cook up something called a quantum Turing machine. And you can say what problems can be decided by a quantum Turing machine in polynomial time or time polynomial of the input size in, for example, with, for example, probability 2/3 of success. So you need to bound the probability of error. Because generally these are more like probabilistic computing, probabilistic classical computing, than they are like deterministic computers. Because they do have the ability to generate randomness internally, because the measurement results are essentially wrong. If you measure a bit that's being prepared in an equal superposition of 0 and 1, you get a random outcome. So it gives you a way of generating randomness within the computation. So this is more like what can be the class of problems that can be solved by a classical computer with access to randomness. So that's or like a Turing machine with some random tip. So this is a class called PP. so bounded probabilistic polynomial time. And for quantum computers, we call the class QP, so bounded polynomial time, bounded error quantum polynomial time. And we believe that well, certainly it contains BPP and it contains P. So there's nothing a classical computer can do that a quantum computer cannot do, in principle, if you can build one of comparable size. But they seem to be able to do much more. So factoring is an example of this, right? Factoring is not known to be in class P, and it's not known to be in class BPP. But it is known to be in DQP. So we do know that quantum computers can solve these at polynomial time, can factor two numbers at polynomial time, or can decide if one of the factors of a number is above a certain constant or below a certain constant in polynomial time, where you can't do that on a classical computer, to the best of our knowledge. And maybe there is some advanced algorithms, and it's realized that in fact there is some classical algorithm that works. But as things currently stand, these classes are distinct. And what you could do on a classical computer, the classes P and EPP, they sit inside the class of things you can do on a quantum computer. There are also some separations that are proven, but not in terms of the time it takes to solve a problem. In terms of the time it takes to solve a problem, we still don't know if you can solve NP-complete problems in polynomial time. And the relationship between the power of quantum computers and classical computers is pretty much like the relationship between non-deterministic Turing machines and regular Turing machines. So that's a really hard problem, and it will probably be a very long time before we're ever able to answer it conclusively. However, there are places where you can prove for sure there is a separation, such as that disordered search algorithm. That runs in a different time than the best possible classical algorithm, and the reason this is a bit different than talking about decision problems is because the search problem, you have to query this external database, right? You have some storage or something that you're looking at different entries in. So this is called query complexity. So how many queries do you need to make to the storage device or to the external database in order to determine where the marked element is? And so we have provable separations for query complexity and for communications complexity. But computational complexity is something that is really, really difficult anyway. We don't really know the power of classical computers, so it's very hard to compare them to the power of quantum computers, except that we know that quantum computers are at least as powerful, and probably a lot more powerful, but we also don't believe that they can solve any complete problems in polynomial time. So there's, if there was I could kind of draw a diagram of the process, but
we've got one question from the Facebook live stream.
Oh yeah.
Yeah. So he asked, do you see quantum computers in our phones in the future? And maybe as an extension, like if you do, how long into the future?
Okay. So I guess there's two ways of interpreting this. One is, do I see them in phones? And the other is, do I see them in our phones? It is hard for me to imagine seeing them in my phone, because presumably I have about 50 years left or less. And that seems, it seems hard. Maybe it's possible, but it's very hard to make predictions beyond even 10 years. So yeah, it's a really long time. In 10 years, no, for sure, you're not going to see it in your phone in 10 years' time. In 20 years' time, probably not either. But I mean, at a certain point, it's just too hard to say where things will go. I do see. I mean, there are ways around Dilfridges. You don't have to have a dilution refrigerator. That just happens to be the best way to do things at the moment. You don't have to have a vacuum chamber you don't have to have one of these giant vacuum chambers for the ion traps. You could try to make some much smaller vacuum module. So you can certainly imagine putting these in more friendly packaging than they currently are. I guess there's going to be a bunch of engineering challenges for that, but it's also likely to be something that depends on the market for actually physically having devices on premises and stuff like that. At the moment, one thing we didn't have in the early days of computing that we have now is we have the internet. So a lot of the companies that are working on this are much more geared towards some kind of cloud model where they'll offer the service over the internet. You just submit your job. It runs it on a device in their facilities and sends it back to you, because you really don't want to be dealing with liquid nitrogen and stuff. Oh, sorry, liquid helium and stuff like that. It's really expensive. So it's I mean, there are potentially ways around these things. They're not a fundamental limit, and there are different ways of building quantum computers, like based on nitrogen vacancy defects, which are these defects in diamond that maybe don't require cooling, and that maybe work okay at room temperature. There's some reasons that people still cool these, but you could potentially do things without cooling them. There may be other technologies, maybe silicon will come along, but at the moment, most stuff is happening either at high vacuum or at low temperatures. Optics is a different situation. So if you try to build something based on photons, you can do most of it in free space. So you don't need a vacuum chamber. You don't need cold temperatures. You could do it with maybe some kind of integrated chip. So there've been some demonstrations of this. The main problem at the moment is to make the best detectors to detect a single photon, and the detectors need to be cold. So the best detectors you get that detect a photon like 99% of the time, they need to be at cryogenic temperatures. So you need to cool them down so they're superconducting. So although the device itself doesn't need to be cold, the detectors are still a problem. There are detectors that work at room temperature with like 60% success probability. But when you start having things that noisy, it adds a lot of overhead. And those devices are still quite bulky themselves. So it's hard to say. Optics is probably the best route for miniaturization at the moment. Silicon maybe also. Superconducting stuff will be required to be cold, so that's a problem. But you could potentially make smaller modules for cooling, things like that. But phones are a long way off.
Any more questions? If not, I think we're like kind of a long way off time.
Thanks.
Yeah. Can we give Dr. Joseph a round of applause?
Can you come back to the slide?
The last one?
No.
Which slide?
This one.
This one.
So we have some pipeline like this. Then we cannot copy over to the quantum.
So most of these probably can, but there's a lot of work that needs to be done. I mean, so you kind of expect certain things, right? So we have quantum Turing machine. We don't have stored programming quantum computer, but in principle, if you can build a quantum computer, you can build a stored program one. We don't have high-level languages, but there's no reason not to believe that they're possible. Error correction, there's some early demonstrations now, but this is a goal that people are really working on for the next couple of years. Compilers, there's a lot of work on that. Microsoft is doing stuff. Rigetti is another, they're a quantum computing startup that went through Y Combinator. They're making hardware, but they're also making compilers. Big quantum software companies, there are some now. Packet switching networks, there's a lot of work on this in places like Delft. OS, not really. Computation is still a bit off. Quantum internet again, there's like some work on this, but it's quite a bit off. Yeah. So people are starting to work in these directions, but we're really at the very, very early days.
Thank you.
Guys, so thank you for staying until the very end with us. Please do help us fill our feedback form. The link Julius will be posting on the screen soon. And just like a small announcement, next week we'll be having a special talk by John Baptiste Kempf. I'm not sure I'm pronouncing it correctly, but he's the CEO of VLC, the Videoland.
For VLC media player.
Yeah, that's quite cool. Yeah, you know the cone, right? Yeah, he's coming down next week, and then you'll be at the hangar. So do check it out.
What's his name again?
Jean Baptiste Kempf. How do you get him? Just ask her.